Okay, this is the last part of the lecture on chapter 4. We're going to talk about how to write Lewis-Dot structures, how to draw valence electrons. For some of you, this might be a review, and for some others, it's a complete new thing you've never seen before, but we'll be using these. We'll learn how to do these, and then we will use Lewis-Dot structures when we determine how to do molecular geometries and electron pair geometries at the very end. So let's get started. When we do Lewis-Dot structures, we only look at valence electrons. And the cool thing about the periodic table is that we can look at the group number. That's why I say remember the group numbers, because they're very, very important and they will help you quite a bit. We look at the group numbers, and that tells us the number of valence electrons, the number of electrons that are found in that last electronic level shell. That is where all of the chemistry happens. If you remember back when we did electronic configurations and we talked about valence electrons, how that we have the core electrons and the valence electrons, and those are the electrons that are found at the very last electronic shell. The group number tells us how many valence electrons we'll have. So boron, for example, is group 3, and therefore it will have 3 electrons, 3 valence electrons. We don't count the other electrons that are part of boron because they are the inner core or the core electrons, and chemistry does not occur with a core electron, so we kind of ignore them for right now. Remember to tell the total number of electrons. We look at the atomic number of boron, but if we want just valence electrons, we look at the group number, not the number right above the symbol of the element in that square. We look at the total group number. If we move on, we have carbon. Carbon is group 4, so there you go. You have 4 electrons for carbon. Nitrogen is group 5, so all of the elements in group 5, no matter what electronic level they're filling, they will all have 5 valence electrons around them. Same thing for 4, same thing for boron 3. Oxygen is group 6, so it has 6 electrons around. Sulfur, which is right underneath oxygen, is group 6, so it will have 6 valence electrons around it. Fluorine, chlorine, iodine, bromine, etc., so group 7, the halogens, they all will have 7 electrons, valence electrons around them. And this is how those electrons are distributed around the atoms. We can look at boron. It has 3 electrons. It doesn't have any unshared pairs of electrons. And it has what we call 3 bonding sites because it can bond in each of these electrons. So it can share each of these electrons, and we'll have 3 places where boron can actually bond with another atom. Carbon has 4 valence electrons around it. No unshared pairs. It doesn't have a lone pair on it that belongs only to carbon. Therefore, it can bond in 4 different places. So it can form 4 single bonds. It can form 2 double bonds, one here, meaning sharing of electrons, 4 electrons with others, but in 2 double bonds. It can have a single bond and a triple bond. Each bond will count as 1 electron coming from carbon. Nitrogen actually has 5 electrons. Well, now that I have 4 electrons with carbon, but I add 1 more, well, I can't just put it over here. Now I'm starting to pair electrons. Remember we talked about how we first we space them out when we fill the electronic configurations, the orbitals, and then we have to pair these out. And because nitrogen has 5 electrons, now we're pairing 1 to form a lone pair. This is called a lone pair. And nitrogen typically will have this lone pair to itself, and then it can bond at 3 different places with another atom because these are unpaired electrons and they're waiting to be paired. Oxygen now has 6, so we're pairing another one. So from one pair, we're adding another electron and we're pairing this one. So it has 2 lone pairs and then 2 single electrons that it can share with another atom. So it has 2 bonding sites. So oxygen or sulfur, etc., although sulfur can change a little bit, but they have 6 valence electrons. They have 2 unpaired or 2 lone paired, one here and one here, and then 2 bonding sites. Fluorine, chlorine, bromine, iodine, etc. Now we're pairing another one, so they have 3 lone pairs around and only one place where they can bond. Because look at the electronegativity, it's increasing as we're going down the period closer to fluorine. Remember, fluorine is the most electronegative, and look at how fluorine will have 3 lone pairs because it is very electronegative. It likes those electrons to itself, and it bonds at only one point, at only one particular site. So it can only form one single bond. Oxygen will form 2 single bonds or 1 double bond, where it will share both of these 2 electrons with the same atom, which also shares 2 electrons. Nitrogen can form 1, 2, or 3, so single bond, a double bond, or a triple bond, etc., etc. So remember these, and remember these are representatives of their groups, and so anything in that group will have the same number of valence electrons and will form similar bonding to any of these. Now, in the main group, we talked about the main group elements. For those elements to be stable, that means they have to achieve the same configuration as noble gases. They have to become isoelectronic, which means they have to have the same number of electrons as the noble gases, either preceding or after them. In this case, because we're talking about covalent bonding, they're not completely giving off those electrons or gaining them, so they're sharing them, which means that they're looking to the noble gas, they're looking to get the same configuration as the noble gas that comes after them. So they will share enough bonds with other atoms, so they'll share enough electrons to get to the noble gas configuration. Fluorine, for example, only has 7, which means to get to the noble gas configuration of neon, it wants an octet. We call 8 electrons in that last shell to fill the shell completely and become like neon. And to do that, it only needs 1 more electron to get 8 around it. Oxygen has 2, 4, 6. It needs to get to neon configuration, it needs 1, 2 more electrons, and therefore it shares 2 electrons with another atom that has 2 electrons to make 8 around oxygen. So it forms 2 bonds, 2 single bonds or 1 double bond. It's the same thing, but it has 2 bonding sites. Nitrogen it needs 1, 2, 3 because neon is right here, or would be in the periodic table. So it needs 3 more electrons to make an octet. We say an octet, or 8 electrons around it. Carbon only has 4 of its own, so it needs to share another 4 with other atoms, which means it will make an octet, or 4 around it, or 8 around it, I'm sorry. So they're all trying to get to the noble gas configuration, so they will share enough electrons to get a full octet rule, right? So the main group, S and P orbitals, will take 8 electrons to get full. Remember we talked about the orbitals? If you count how many you can fit in the S and the P gets 6 and S gets 2, which means that together, the S and the P orbitals take a total of 8 electrons. That's why octa means 8. This is the octet rule, that elements will share enough electrons with other elements that they can make 8 electrons total around them, the octet rule. Now, this is how we follow the rules that we follow to write Lewis-Dawes structures for molecules. The first thing that we do is we add up all the valence of electrons for all of the atoms so that we determine a total number of electrons. Then we write a skeleton equation based on the most bonding sites. So whoever has the most bonding sites will typically be the central atom. So if I have a carbon, for example, and a fluorine, fluorine has only one bonding site, but carbon has 4. So carbon will be my central atom and fluorine will be terminal, meaning will be at the end because it can only form one bond. It cannot form multiple bonds because it only needs one more electron to share to form 8 around it. But carbon has 4 sites it can bond. So because it has the highest number of bonding site, typically it will be what we call a central atom, an atom that will be in the center, and then you'll have other atoms around it. So we look to write skeleton equation, or how the atoms are bonded to each other. We look to the most bonding sites. Those that have the most bonding sites will be in the center. Those that have the fewest, like hydrogen, for example, only needs one bond because it only needs one more electron to fill its 1s orbital. It can only take two electrons around hydrogen because hydrogen is the 1s is filling the 1s orbital, which only takes 2 electrons. So typically, what you also have the least of, so if you look at the number of atoms for each element, whatever you have the least amount, that will be your central atom. And whatever you have the most, that will be around the central atom. That's another helpful tool to look at. And then you place 2 electrons for each single bond, right? If one single bond, which is denoted with a line, will be equivalent to 2 electrons because it's 1 electron from one atom and 1 electron from the other atom to form a bond, which is written as one line. And then you have to reduce the total number of electrons by each bond by 2 for each single bond. Now, if we follow this logic, a single bond has 2 electrons, a double bond will use up 4 electrons, and a triple bond will use 6 electrons. And then if you have unshared pair of electrons, you'll put 2 electrons there for each unshared pair. We use then double and triple bonds to satisfy the octet rule on central atoms. Remember, the terminal atoms, those that are at the edges, can only take one single bond, but the central atoms, the atoms that are in the middle, they will need to have 8 around them, and they can actually accommodate several single bonds, or single and double bonds, or single and triple bonds, etc., etc. I have made a video on how to do these 2 problems, and we will do many more in class just so that we get the idea of how to write Lewis-Dawes structures. But watch this video on YouTube, and if you have any questions, we'll cover those in class. There are exceptions to the octet rule, which means that sometimes not all atoms follow the octet rule, meaning they don't necessarily fit 8 electrons. For example, we have an odd number of electrons. Nitrogen monoxide here, this element, commonly named as nitric oxide, has an odd number of electrons. So it doesn't follow the octet rule. Sometimes we have an unfilled octet, like any compound that has boron in it. Boron doesn't need 8 electrons around it. It's actually happy with 6. And then there are some elements like phosphorus and sulfur and others that can fit more than 8 electrons around that central atom. But note, for example, here, phosphorus is my central atom because if we look at phosphorus, it's group 5 with nitrogen. So it will have a lone pair typically and 3 single electrons to bond, three places to bond, whereas chlorine only has one place where it can bond, one bonding site. And so phosphorus will be my central atom because it has more bonding sites. Also, you can tell by, I have only one phosphorus atom and I have 5 chlorine atoms. That means that what I have the most of, which is chlorine, will be on the edges, and what I have in the least of, which is phosphorus, will be in the central atom, will be in the middle, and the chlorines are all around the phosphorus. Once again, I've made a YouTube video on how to do all 3 of these and how to show you how to do Lewis-Dot structures for an odd number of electrons, unfilled octet, or a larger than octet rule. Okay. I also have a video on how to figure out the identities for each of these elements that are depicted as X here, and how to go about doing problems like this. Now, the last part of chapter 4 will cover the geometry of molecules. We talk about 2 different geometries. We talk about the electron pair geometry and the molecular geometry. The electron pair geometry can be the same as the molecular geometry, but it can also differ. And how do we figure this out? We talk about electron pair geometry by looking at the number of electron dense areas around the central atom, or the groups around the central atom. So if we have only 2 groups around the central atom, that means that I have a linear geometry. The idea is that whatever is bonding, remember that these are electrons, and electrons are negatively charged. Therefore, whether you have a lone pair or a bond, a single bond or a double bond, those electrons are going to occupy a 3-dimensional space around that central atom, such as they want to minimize the contact between them because they repel. So they want to be as farther apart as possible. If I only have 2 groups like this one here, well, I can place them, the farthest apart I can place them is in a 180-degree geometry. So if this angle is 180 degrees, if this angle is 180 degrees. So I take the 360 degrees around this dot, which is my central atom, and I divide it by 2 because I have one group here and one group here, so 2 groups around that central atom, and gives me 180 degrees. That's the angle in which these groups are going to be, because they're as farther apart as possible when they're at an 180-degree angle. Because of that, the electron pair geometry is a linear geometry. They're all in a line. And because I don't have any lone pairs around this central atom, I have only 2 groups, 2 bonds. That means that because I have no lone pairs, and there are no exceptions for 2 groups, the molecular geometry is also linear. So for 2 groups around the central atom, the electron pair geometry is the same as the molecular geometry because I don't have any lone pairs. Now let's look at 3 groups around the central atom. I have 1 group, 2 groups, 3 groups. When I do electron pair geometry, that only looks at the number of bonding or groups around the central atom. It doesn't look at whether they're bonds or whether they're lone pairs. It just looks at how many groups. And because I have 3 groups now instead of 2, what I do to calculate the angle between these would be to take 360 and divide it by 3. That gives me 120 degrees each. So each of these angles between these bonding groups these groups around that central atom have to be 120 degrees to be the furthest away from each other. This is my electron pair geometry for any molecule that has three things around it, whether it's a lone pair or two bonds or three different groups, three different atoms. That is my electron pair geometry is the same. And for three groups, the electron pair geometry is going to be trigonal planar. Now, if I go to look at the molecular geometry, I can have two different molecular geometries with three groups around the central atom. If I have three groups around the central atom and I have three atoms around the central atom, all of these groups are atoms. That means that my molecular geometry is the same as my electron pair geometry, which means it's also trigonoplanar. Now, if I replace that one of these, doesn't matter, but one of these atoms with a lone pair on that central atom, so I have a lone pair instead of this atom here, and then I have two atoms, so one lone pair and two atoms, I still have three things around my central atom, so my electron pair geometry is still trigonoplanar. That doesn't change because that's determined by how many things you have around that the central atom. So I still have three things around that central atom, even though I have a lone pair now, but it's 1, 2, 3. So three groups around the central atom. That makes for a trigonoplanar electron pair geometry. But the molecular geometry is now slightly different because the lone pair, turns out that the lone pair occupies more space than if I just had an atom here. And that means that this lone pair is going to repel these electrons of these bonds here a bit more, which means that they're going to be pushed a little closer together, than if I just had an atom here. That means that this molecule, those angles are not going to be quite 120 degrees. They're going to be what is called bent. So the molecular geometry can, with three things around the central atom, can either be trigonoplanar when those three things are all the same, they're atoms, or it will be bent if I have two atoms and one lone pair. Now let's look at what if I have four groups around the central atom, and we'll quit there. We're not going to do 5 and 6. Those are for higher class chemistry classes. But if we have four groups, 1, 2, 3, 4, once again, my electron pair geometry is not going to change because I have four things around the central atom. And if I divide the 360 by 4, I get 109.5 for all of these angles. And we call that a tetrahedral geometry. Here's what a tetrahedral geometry looks like. You have that central atom bonded to four different groups, four different atoms, and it looks like a pyramid with the central atom in the middle, and then on the ends here you have atoms. The trigonoplanar is one triangle. They're all in the same plane with a central atom in the middle of the triangle, and at the edges you have those three atoms. Okay, now if you get rid of that atom, these two will be a little closer to each other, and therefore you have a bent molecule. But let's talk about tetrahedral. So tetrahedral electron pair is always going to be four groups around four. So if you count 1, 2, 3, 4, four things around the central atom, it's always going to be tetrahedral for the electron pair. Same thing for these two, right? The electron pair never changes because it only looks at how many groups, how many things you have around the central atom. So it's going to be linear, trigonoplanar, or tetrahedral, depending on whether you have 2, 3, or 4 things. Now the molecular geometry changes because it will take into account whether all of these are the same. So if you have atoms or if you replace the atoms with lone pairs. Now let's look at the case when you have four things around the central atom and they're all atoms. In that case, you have no lone pairs, which means that the molecular geometry equals or is the same as the electron pair geometry. So both are tetrahedral because you don't have a lone pair. You have 4 atoms around that central atom. If you replace that one atom with a lone pair now, you don't have a tetrahedral molecular geometry. The electron pair geometry is still tetrahedral because you have 1, 2, 3, 4 things around the central atom. But the molecule, so the molecular geometry, changes because that lone pair wants to occupy more space, so it pushes these electrons, it repels these electrons of these 3 bonds with those 3 atoms further in towards each other. So it doesn't have a 109.5 degree angle anymore. We call this molecular geometry trigonal pyramidal, like a pyramid with that central atom on top and then these 3 on the edges. Now if I take this atom and I replace it with another lone pair, so I have 2 lone pairs, that molecule, so the electron pair geometry is still tetrahedral because I have 1, 2, 3, 4 things around the central atom. That number doesn't change. What changes is a type of group I have around the central atom. And that type of group determines the molecular geometry, not the electron pair. That's always the same. But because now I have 2 lone pairs, those lone pairs are really going to repel each other and these 2 bonds because they really want more space. They occupy more space. So these 2 atoms are going to be pushed in towards each other even more. And we call this molecular geometry bent. So the tetrahedral electron pair geometry can have 3 molecular geometries depending on how many lone pairs you have. If you have none, you have tetrahedral. If you have 1 lone pair, it's trigonal pyramidal. If you have 2 lone pairs, then you have a bent geometry. That is why it's important for us to learn how to draw Lewis dot structures, because that will tell us if we have lone pairs on that central atom. And if we have lone pairs, then that will change the molecular geometry. And then the last slide that I have here for chapter 4, once again, I have the electron pair geometry and molecular geometry that we're going to talk about in this class with 2 groups, 3 groups, and only 4 groups around the central atom and no more. And then I have given you examples of each. So I have worked out problems, how to do Lewis dot structures and how to determine electron pair geometry and molecular geometry for each of these. So 2 groups around the central atom, but I have 2 single bonds, 2 double bonds, or a single bond and a triple bond. So I have these worked out. I have these for 3 groups around the central atom, and these examples for 4 groups around the central atom. So watch these videos and see how to do these examples and bring your questions to class. This concludes the lecture on chapter 4.